This is the last lecture in Chapter 14, Kinetics, and this wraps up a number of topics, starting with collision theory, the Arrhenius equation, and mechanisms of a reaction. Collision theory is simply a conceptual idea, and what it says is that in order for reactants to react, they must collide with one another. And it can't be just any old collision. There are two requirements for an effective collision. One is that the reactants collide with enough energy to break the bonds that need to be broken, and that'll later be called activation energy. And the collision must also occur with the proper orientation for new bonds to form. This is a typical reaction progress graph that shows the potential energy of a reaction as it proceeds. This type of graph is so commonly used in chemistry, so you'll see it through the remainder of the semester. And there are potential energy along the y-axis, and reactants are represented. They're the first substance that's represented, so their collective potential energy is marked. Then at the very end, on the far right of the graph, are the products. In this particular graph, it is an exothermic reaction because the energy level of the products is lower than that of the reactants, and so all of this extra energy is released, so it's exothermic. Now, what we're going to talk about in this chapter, however, is the activation energy. And that is the difference in energy between the initial reactants and the highest energy point, which is called the activated complex. Every reaction has an activation energy, regardless of whether it's exo or endothermic. And as a matter of fact, exo-endothermic has nothing to do with the size of the activation energy. But we care about activation energy because it is that determines the rate of a reaction, okay? So just imagine you have different size hills to run over, okay? Your rate from getting from one side of the hill to the other is going to be quite a bit faster if this hill is smaller. Same thing with a chemical reaction, okay? The larger the activation energy, the slower the rate of reaction. I said also that collisions need to occur with the correct orientation. So look at this reaction as an example. One of the products is molecular chlorine. And so in order for this and a collision to be effective, the two reactants must collide in such a way that the chlorine atoms are in close proximity to each other so that they can form the new bond. Okay, so collisions that result in product formation are called effective collisions. The higher the frequency or the more collisions there are per unit time, the faster the rate of reaction. All right, probably the single most important factor in the rate of a reaction, aside from the activation energy, is the temperature at which the reaction occurs. That makes sense because when you heat something up, that increases kinetic energy. Kinetic energy is the energy of movement, and the more you have the molecules moving, the more likely they are to collide and react. So the higher the temperature, the faster the rate of reaction. Which leads us to the Arrhenius equation. A scientist named Arrhenius studied the effect of temperature and activation energy on the rate and came up with a mathematical relationship between rate constant, activation energy, and temperature. This form of the Arrhenius equation we won't use directly, but I did want you to see it. So the symbol for activation energy is E sub A. R is the universal gas constant. It's important when you use any form of the Arrhenius equation to use the value for gas constant with units of energy, units of joules. And that particular value that you need to use for these calculations is 8.314. All right, and of course, E sub A is activation energy. Temperature must be in Kelvin. One more graph to interpret. This graph has energy along the x-axis, which makes it a little bit counterintuitive, at least for me, and number of molecules or fraction of molecules along the y-axis. And so this type of graph is used to show the effect of temperature on the fraction of molecules that have adequate energy to undergo reaction. So, for example, look at the blue curve. It is occurring at a certain temperature. So the average kinetic energy at this temperature would be whatever the scale would show it would be. And the energy needed to react, that is the activation energy, is here. So anything below the activation energy is not going to have adequate energy to react. The only amount of reactants that can react are the reactants that have equal to the activation energy or greater than the activation energy. However, now if you increase the temperature, so now look at the red line, that means that the average kinetic energy of the molecules is higher, and because of that, there'll be a much greater fraction of reactants that are able to react. Okay, so here's another version of the Arrhenius equation, and this is more commonly used and one that you'll need to be familiar with. So they basically just took the natural log of both sides of the Arrhenius equation, and now it's in the format of a line. So y equals mx plus b. So you plot natural log of the rate constant on the y-axis. My dogs are getting ready to bark. And plot 1 over t on the x-axis. And look what the slope's going to be. In this case, the slope is equal to minus activation energy divided by the universal gas constant. So here's a sample question you might be asked on a quiz or a test. What is the activation energy for the reaction represented in this graph? So what do? The first thing you would do is find slope. Hopefully you'd realize that this is an Arrhenius graph because natural log of the rate constant's on the y-axis, 1 over t is on the x-axis. That reminds me, by the way, I would, in studying for this next exam, make a note of all of the types of graphs I've shown you and what the x and y axes are for each of them and what you can get out of them. Because you remember from the last test how many people got confused about what the axes should be labeled. All right, so if you remember from the Arrhenius equation, the slope of this type of graph is minus activation energy over R. So since the problem's asking us to find activation energy, we need to find the slope. So pick any 2 points on this graph. So here we go. So if we pick 2 and minus 2, okay, and drop those points down to see what x-axis corresponds to it, 1 over t. So the change in y, those are the 2 points I picked, and the change in x for those same 2 points would be, I estimated at 0.00142. Now it looks like 0.00145, whatever. This isn't a very accurate scale. And minus the other one is 0.0017 something. So when I do the calculation for the slope, I get somewhere around 13,000. So then what you do, so first you find the slope, then you set the slope equal to what it's equal to in the Arrhenius equation, which is minus activation energy divided by R. Notice at this point that you have minus on both sides, okay? The slope of an Arrhenius graph will always be negative, so you're always going to have a negative sign there. The equation has a negative, so I just removed the negatives. So to solve for activation energy, you're going to multiply both sides by 8.314, and that gives us an activation energy of 110,853 joules, okay? Notice the units you get from this Arrhenius equation are joules, and that's simply because R has units of joules. So if the problem asks you for kilojoules, you're going to have to do a conversion. And then as my dog drinking water in the background, they're being especially noisy tonight, sorry. Yay, and yet another form of the Arrhenius equation. If you do not have an Arrhenius graph to work with, you could also figure out activation energy if you were given two different temperatures and the rate constants associated with those two different temperatures. There are so many different versions of this two-point Arrhenius equation. They all work, okay? I will give you one of the forms on your exam, but there are ones with a negative sign too. There are ones with K2 on top. None of that matters, and I'm going to remind you what really matters. So there's one with a negative EA, but in that case they have to switch the T values. Okay, so mathematically they're all equivalent to each other. What is important when you're working with a two-point Arrhenius equation is that whatever value you plug in for K1, and I don't care if it's the high value or the low value, but whatever value you decide to put on the top and call K1, the temperature that goes with that K1 must show up here in the equation. So that's important. In order to know what rate constant goes with what temperature, you need to understand that the higher the temperature, the faster the rate. Okay, so the higher K, the higher T is. So the fastest K, the largest K, also has the highest temperature. And now there are just a bunch of places to make minor math errors, especially in this 1/T. So practice some of these just to kind of get the kinks out. Here's a sample for you. And if you didn't already work this in class, I strongly suggest you work it. I've had so many students in the past look at the two-point Arrhenius equation and say, okay, that's just math in my calculator, I can do that. Don't count on it because a majority of you end up making silly mistakes and you don't have time on a quiz or test to figure out what little glitches you're going to run into. So try to make yourself do it now. And remember, whatever value you give to the large K also has to have the large temperature. All right, so here's the two-point Arrhenius equation. And because it said the rate doubles, we're just going to randomly call, we're going to call K1 2, and we're going to call K2 1. Okay, now I just have to notice this is a version without a negative sign here. Now I just have to be careful that I put temperatures in the right places. So I called K1 the larger rate. So that means that T1 has to be the larger temperature. K1 goes with T1, K2 goes with T2. So that means T2 is the lower temperature, which would be 25 and 273, which is 298 for the lowest temperature. All right. And now the higher temperature goes in here for T1. And when you add 273 to it, you get 309. And of course, our value is 8.314. and now you solve for activation energy. All right, so in this case, again, your answer is going to be in joules. And so if the problem asks for kilojoules, you're going to have to do the conversion. All right, just a quick side trip into catalysts. We've been talking about how the rate of a reaction depends on activation energy, and I've also mentioned catalysts and the fact that they speed up the rate of a reaction. Well, the reason that catalysts speed up the rate of a reaction is because they lower the activation energy. So, just like the analogy I like to give, if you had a large hill and you had to get to the other side of it, you could run all the way up to the top and all the way back down. That'd be quite a bit of energy you'd have to put out to get over that hill. Or if somebody had the proper tools and was nice enough, they could drill a hole all the way through the bottom of the hill, and you could simply run through that tunnel. Okay, that would be providing a new pathway and lowering the activation energy. That's what a catalyst does. It lowers the activation energy by providing a new and different pathway for the reaction to occur. There are two types of catalyst. There is a homogeneous catalyst, which is a catalyst that is in the same phase as the reaction taking place, so you can't tell it's there visually. Then there is a heterogeneous catalyst, and that's a catalyst that's in its own separate phase, and it's usually quite obvious. So it might be something like, I don't know if you ever heard of activated carbon, but sometimes that can help this or speed up a reaction. Metal, pure metal can often speed up a reaction. So there are some reactions where literally a sheet of metal will be put in to serve as a catalyst. All right, the final of the three topics in this lecture is reaction mechanisms. A mechanism is a series of steps that the reactants undergo to reach the product. So you are used to seeing what we call overall balanced reaction that show just the reactants and then the final products. It turns out that most reactions undergo a series of steps. So it might be, maybe A reacts with itself to give some weird Q intermediate, and then Q reacts with B to give C and D. I mean, you just don't know, okay? So if you know the mechanism, there's some pretty cool things that you can do. I think the coolest thing you can do if you have the stepwise mechanism is you can directly write a rate law from a step within a mechanism. And so if you had an overall balanced reaction, so I'm making this up. Okay, so let's say you had that reaction and I asked you to write the rate law. You would write, okay, rate equals K times concentration of A raised to some power, which you don't know until you do an experiment, times the concentration of B raised to a power. So these powers, these exponents or order of reactions, you really can't say anything about them in an overall reaction until you do an experiment. In an elementary reaction, that's stepwise parts of a mechanism, you can write the rate law with its order directly from that mechanistic step. So let's look at this one, for example. You could write the rate law for this particular step, saying it's some rate constant times A plus A plus A is the same thing as 3A, right? Times concentration of A cubed because of this coefficient of 3. So you can do that for elementary steps. Just a quick vocabulary thing for you. The individual steps in a mechanism are referred to, you might be asked, what's the molecularity? If there's only one reactant in a step, it's called unimolecular. If there are two reactants, it's called bimolecular. If there are three reactants, it's called termolecular. So here's a straightforward example of a mechanism. Here's the overall balanced reaction for the formation of nitrogen dioxide from nitrogen monoxide and oxygen. And again, if I asked you to write out the rate law for that, you could write this much. Rate constant times the reactant nitrogen monoxide raised to some power times the concentration of oxygen raised to some power. But you couldn't say anything about X and Y until you did experiments. However, if you are given the mechanism for this reaction, you can see it occurs in two steps, and they're called elementary steps, and both of these are bimolecular elementary steps because they each have two reactants. There are two nitrogen monoxides in the first one, and there's one N2O2 and one O2 in the second. So we could write rate laws directly, remember, from each of the elementary steps. So for step one of the mechanism, the rate law that is compatible with it is shown right here. Remember, you can take the coefficient and turn it into an exponent. Again, this is only for elementary steps. This second one, you can do the same thing. You could write the rate law for it. Be careful to assign different rate constants to the different elementary steps in a mechanism. Now, the only step that is truly important as far as the rate of reaction goes is the slowest step. The slowest step is called the rate determining step. Just like if you were running a relay race, if you had a really slow person in the middle of your relay race, it really wouldn't matter how fast you ran, because this person would be a bottleneck and determine your overall ranking in the race. Same thing in a chemical reaction. The slow step serves as a bottleneck, and it basically determines the rate of the entire reaction. There is a lot of information in this slide, so I'm going to go methodically and slowly through it. So in blue at the top is the overall balanced reaction. In red below that is the mechanism, the stepwise elementary steps. And to the right of them are the rate laws, the differential rate laws that you can write for each of the elementary steps. Now, in a problem, typically you will be told which of the elementary steps is the rate determining step. And they'll just basically say the slow step is such and such. So in this case, the first elementary step is the rate determining step. And so that is the step that determines the rate of the entire reaction. So before we use that to work problems, I also want to point out this energy diagram. If you know the individual elementary steps in a mechanism, you could write a more detailed energy profile. So for example, this reaction we know has two steps. Every single step has to have its own activation energy. We also know the first step is the rate determining or the slow step. So we know that the first step has to have a larger activation energy than the second step. Now, notice here that the activation energy for the second step is from the intermediate that's formed after the first step up to the activation energy. So if you're finding the activation energy of a second, third, or fourth step, don't go all the way back to the energy level of the reactants to figure it out. So because the first step is slow, that means the rate law for the entire reaction equals the rate law for that slow step, which is this. Okay. Now, the only glitch here is in the harder problems that have to do with mechanisms. Sometimes the rate law that you get from the slow step has a substance that is not a reactant. So once you establish the slow step and you look at the rate law for that slow step, make sure that it's in terms of reactants. So this particular one is in terms of nitrogen dioxide, and that is in fact a reactant. So you'll see in a few slides examples when that's not the case and you have to do additional substitution. So just in a neater form what I just said, since the first step is, you were told that it's the rate determining step, the rate law for the first step as well as the overall mechanism is this. Now, here's where potential challenge comes in. If the problem says that the second step is the slow step, that would mean the rate law for the entire reaction would equal the rate law for that second step. So I want you to look in this case, pretend like the second step was rate determining. So write down the rate law for the second step. Remember what I said, always look and make sure that the substances in the rate law are reactants. Well, oxygen certainly is a reactant, but N2O2 is not a reactant. We'll learn about something called an intermediate later. Okay, that's something that's formed and destroyed in the middle of a reaction. But since it's not a reactant, it's also not a product, it's got to be an intermediate. You cannot present rate laws in terms of substances that are not reactants. So if you haven't, because you can't measure, the whole idea of a rate law is to be able to measure concentration changes and predict rates. So, but if you have a substance that's not even a reactant, you're going to have a real hard time following. It's impractical. So when that occurs, we have to do a substitution so that all of the substances presented in the rate law are in fact reactants. This part is quite complicated, so you may have to listen to it a couple times and or read your book in addition. All right, so we're still going to make the assumption that the second step is the rate determining step. So if the second step is rate determining, that means the first step is fast. If a first step is fast, that means it reaches equilibrium quickly. What the heck is equilibrium? We're going to talk about it toward the end of the semester, but it is important at this point to understand that equilibrium means the rate of a forward reaction equals the rate of the reverse reaction. So it's not saying anything about the amount of product or reactant. It's talking about rate, how fast the forward reaction is going. So clearly this would be a reversible reaction if there's a reverse rate. And the formation of the product, the destruction of it are occurring at the same rate. So if that's the case, if the rate of the forward reaction equals the rate of the reverse reaction, we can write rate laws for both the forward reaction and the reverse reaction. Here is the first step, which we are just saying now happens to be the fast step. It is not the rate determining step, but it's going to help us get our rate law in terms of all reactants. So the fast step, again, we're going to assume it's at equilibrium. Therefore, we can say the rate of the forward reaction equals the rate of the reverse. So what is the rate law for the forward reaction here? Okay, it is K times concentration of NO squared. All right, now that's the rate law you would write for the reaction going in the normal direction. What do I mean when I say the reverse reaction? Well, it's assuming the product is the reactant and it's going this way, back to make more reactant. So if you want to better visualize a reverse reaction, simply write it in reverse. So whatever the product is becomes the reactant. Whatever the reactant is becomes the product. Okay, so this is the reverse reaction. So now you're going to write a rate law for the reverse reaction. So we're going to call that KF for the forward reaction and K reverse for reverse reaction. What is the reactant for the reverse reactant? It's N2O2. So now you have that these two things equal each other, okay? K of the forward reaction times nitrogen monoxide equals K of the reverse reaction times concentration of N2O2. Why are we doing this? Because the rate for the rate determining step, the second step in this case, remember, is in terms of an intermediate, and the rate law has to be expressed only in terms of reactant. So by setting up this equality for the first step, we can find a substitution value for this intermediate N2O2. So look for a minute over to the left, and this is the rate of the forward reaction equals the rate of the reverse reaction. So now simplify this equality to solve for N2O2 because that's what we're trying to get rid of in our overall rate expression. So if you substitute, you get the N2O2 equals this big thing. So now you're going to go back to the rate law for the rate determining step, and wherever there's an N2O2, the intermediate, you're going to substitute in this whole thingy here. So here is the original rate law for the rate determining step. And our objective was to get rid of this intermediate species. So we set an equilibrium for the fast first step, and then we plugged in what we saw for N2O2, and we get this. So now if you go back to the reaction, all of the substances in the rate law are in fact reactants, so that's good. That was our ultimate goal. So now instead of writing all these crazy separate rate constants, you can just call them some new K. A lot of times when those are combined, the textbook will just say what they call K prime. Okay. So our rate law now for this reaction is as shown here. Here's another type of problem that you're likely to see concerning mechanisms. So here's an overall balanced reaction. Now in this case, rather than telling you to find the rate law, they're giving you the rate law. Somebody's already explored it and found it. And they're also giving you the mechanism, the stepwise elementary steps to make this. And they're asking you determine which of these steps is the rate determining step. So I suggest turning off the video for a minute and see if you can figure that out, okay? How could you possibly know which one of these two elementary steps is the rate determining step? My hint to you is remember that you can write rate laws directly from elementary steps. That's my hint. So play around, see if you can figure it out yourself, and if you can, you're in an awesome place. If you can't, that's fine. Just listen to the rest and you'll get it eventually. Alrighty. So since you can write rate laws directly from elementary steps, let's go ahead and write the rate laws. The rate law for step 1 would be some rate constant, whatever it is, times the reactants. So for step 1, the reactants are nitrogen dioxide and ozone, O3. The exponents are 1 for both of them. And the rate law for step 2, some rate constant. The reactants for step 2 are NO3 times NO2. So what you do now is you ask yourself, do either of the rate laws written for the elementary steps match the rate law that's already been demonstrated for this overall reaction? Well, yes, step 1, the rate laws match exactly. That tells us that step 1 is the only step that is determining that rate, and therefore it is the rate determining step. Take a look at the rate law we got for step 2. Okay, it does not match. So that just confirms that step 1 is the rate determining step. Now it's your turn for sure. Here's an overall balanced reaction. Here's the proposed two-step mechanism. They tell you which one is the rate determining step. So write the rate law for this reaction. And remember, this is not as easy as it might first look, because once you write the rate law for each of these elementary steps, the one that you choose to be the overall rate law must only have reactants in the expression, reactants from the overall balanced reaction. So if the rate law you decide is representative has anything other than nitrogen monoxide and oxygen in it, you have to do that mathematical substitution, assuming the fast step is the equilibrium, etc. All right, so here we go. Since step 2 is the slow step, or the rate determining step, we have to start by using the rate law we get derived from that second rate determining step. And that would be some rate constant times N2O2 times O2. I'm hoping then that you looked at this rate law from the rate determining step and said, okay, are the substances in this rate law both reactants? No, N2O2 is not a reactant, it's actually an intermediate. And so I got to get rid of it. Okay, rate law has to be in terms of only reactants. So I've got to make that assumption that since step 1 is fast, it establishes equilibrium, which means the rate of the forward reaction equals the rate of the reverse reaction for elementary step 1. Okay, the rate law for the forward reaction is, we'll just do Kf times nitrogen monoxide squared. So I'm just looking at this. The rate for the reverse reaction, K reverse times concentration of N2O2. Now, N2O2 is what we're trying to find a substitution value for. So we need to rearrange this equation so that we know what we're going to plug in every time we see N2O2 up here in this rate law. So N2O2 would be Kf over Kr times nitrogen monoxide squared. So this whole thingy expression gets plugged in for N2O3, and when you shake everything out, cross out what's the same, here is the rate law. Now, a third type of question, and this one's quite easy. You might be given an overall reaction and a choice of 3 or 4 mechanisms. So the question might say, which of these mechanisms is possible? How would you know that? Okay. If a mechanism has been proposed, there are 2 conditions that must be met. Number 1, when you add up the elementary steps and literally add them up, so all the reactants get added together and then all the products get added together. The elementary steps must add up to give the overall reaction. And as we just demonstrated in the last problem, the overall rate law that was found experimentally has to be one and the same with the rate law predicted by the rate determining step. So let me show you what I mean when I say the elementary steps must add up to give you the overall reaction. Here is a balanced overall reaction, and here's the proposed mechanism. If I were to ask you does this proposed mechanism, is it possible? Does it meet the requirements? The first thing that you would do is add together all of the reactants of the two steps. So I'm just starting here, H2 plus ICl, and keep adding reactants, plus whoopsie daisy, plus HI, plus ICl, and then arrow, and then add all the products. So yields HCl, and then plus HI, and then the products down here in the second step, plus HCl, plus I2. Now you want to cross out anything that's the same on both sides and also combine like terms. So right away, the only thing I see that is both on the reactant and product side that I can cross out is HI. And now I'm going to combine like terms. I have two ICLs on the reactant side and I have two HCl's on the product side. So let me rewrite this. So I have H2 plus 2 ICl yields 2 HCl plus I2. Okay. So now when you add the two mechanisms together and simplify it, it must match the overall balanced reaction, which in fact it does. So it meets requirement 1. Requirement 2 is that the rate law you get from the slow step must match the actual rate law, okay, that's experimentally determined. Now this problem does not tell you what the slow step is, so you can't validate it. But basically, you would have to write the rate law from the slow step and make sure that it matches the given rate law in the problem. And finally, hopefully you can take a minute and read the words in this slide that I've now scribbled completely over. But make sure you understand what an intermediate is, okay? You can detect an intermediate only by looking at the elementary steps. So the definition of an intermediate is something that does not appear as a reactant or product in the overall reaction, but is formed during the reaction and used up during the reaction. So it looks like HI does not appear in the overall balanced reaction, and yet it's formed during the reaction and then it's used up in the next step. So when everything's simplified, they cross out. That makes HI an intermediate. Do not confuse an intermediate with a catalyst, okay? A catalyst is there from the beginning. So if you have an overall reaction, A plus B gives C, if most of the time they just write the catalyst over the arrow. But if you see something funky, we'll just say Z, and the reactant side and on the product side, okay, that means that's a catalyst. Catalysts are there in the beginning, they're there at the end, they don't get consumed.